Hi everyone, I'm Baichun. Unfortunately, all the authors couldn't be here, so I will be presenting for them instead. Today, I'll be showing you our paper towards distance adaptive wireless charging. So wireless charging has been evolving since the 1890s. Continued research highlights just how important and challenging it is. Current wireless charging technologies have typically adhered to a singular approach, choosing between near-field coupling or far-field radiation. Near-field coupling systems are highly efficient but very limited in range, whereas far-field radiation systems work over long distance, but their efficiency suffers. Recently, several efforts have explored the field of a multi-mode wireless charging, such as combining inductive and resonant techniques at low frequencies or designing reconfigurable resonators and topologies for mode switching and efficiency optimization. However, most of these approaches are limited to near-field operation, with effective charging distances restricted to just a few centimeters. Also, the system that supports long-distance wireless charging at the room scale requires impractical setup like full room metal surfaces. Fortunately, we found that near-field and far-field modes complement each other in power transfer efficiency at different distances. When the device is closer to the charger, the near-field mode achieves a higher power transfer efficiency compared to the far-field mode. Conversely, the far-field mode is more efficient when the device is further away. So we imagine a mode-adaptive smooth wireless charging in the future. Picture a charger mounted that automatically switches the charging mode for your phone and other devices according to the distance's location to ensure continuous high efficiency during the charging process. For the above purpose, in this work, we propose ChargeM. It's designed to utilize a single transceiver system that operates at two disparate frequency bands to support both near-field and far-field wireless power transfer. And we involve a single metal surface operating at the same dual band frequency as the transceiver coil to further enhance power transfer efficiency. The basic idea sounds simple. While translating ChargeM into a practical end-to-end system requires us to tackle various challenges. Initially, the challenge lies in designing a receiver RX coil that is sufficiently small to fit within the compact dimension of modern mobile devices, while allowing the TX coil to be larger to improve efficiency. Traditional design principles suggest it is challenging to make coils of drastic different sizes operate efficiently at the two different frequency bands for multi-mode functionality. To solve this problem, we first introduced the general idea of achieving dual band resonant design for transceiver coil and metal surface. Actually, the dual band principle in metal surface assisted wireless power transfer relies on tuning the capacitive reactance through capacitors connected to the transceiver and metal surface units. At high frequencies, the connected capacitors behave like a short circuit, leaving the resonant behavior determined by the intrinsic structure parameters, while at lower frequencies, their influence becomes significant, allowing resonant adjustments via capacitor values. This frequency-dependent impedance behavior enables the system to support both near-field and far-field wireless charging modes. In this work, we chose the two resonant frequency bands to 13.56 megahertz and 300 megahertz as example to validate the multi-mode characteristics. These frequencies can be adapted to other bands depending on our needs and structural design. Our choices of these frequencies in this work consider small size of receiving devices, adheres to the licensed frequency band for wireless charging, and aims to minimize path loss for interference issues. To make these two coils of drastic different size operate on the same two disparate frequency bands, the transmitter coil is first designed to resonate at both 300 megahertz and 13.56 megahertz by tuning its structure and capacitance without altering its physical dimensions, according to the above multimode principle. The receiver coil is then miniaturized to just a few centimeters by independently optimizing key geometric parameters such as inner diameter, wire diameter, and turning spacing, while maintaining dual band resonance. This design structure allows both large and small coils to function effectively across the two frequency bands, facilitating efficient multimode wireless power transfer. Also, the meta surface is designed to operate at the same two frequency bands as the transceiver coil by scaling its geometry and tuning capacitance, following the multimode principle. To meet the additional requirement of low loss, high directional control in the near field, so spiral-shaped resonator, meta-atoms, and low-loss substrates are used to achieve high permeability within minimal attenuation. The final meta-surface consists of a symmetrical array of these meta-atoms, enabling effective beam focusing at both frequency bands. Here we present the simulation results of the transceiver coil. It can be observed that when the capacitance values are set to 8.7 picofarads for the large coil and 90 picofarad for the small coil, both coils achieve resonance at the same two target frequency bands. In the meantime, we construct the meta-surface with 8x8 meta-atoms and simulate its positive effects in both near field and far field. The results shown in the figure demonstrate that meta-surface can successfully steer a magnetic field and focus the electric field to multiple small receivers at different locations. After achieving efficient power transfer between the TX and RX coil, the next step is to build a complete multimode wireless charging system. This requires a source circuit that can generate precise AC signal at two disparate frequencies while delivering over 20 watts of power. However, typical MOSFETs fall short due to frequency inaccuracies and limited voltage tolerance at high frequencies. To address these, we use an advanced enhanced gallium nitride transistor to build a self-oscillating circuit at 300 megahertz and an LTC 6903 chip to generate a 13.56 megahertz signal. This setup ensures accurate oscillation at both frequencies. The signals are then amplified using multiple commercial amplifiers and combined into one channel with dual band combiner before being fed into the TX coil. To ensure the rectification efficiency of a load circuit at the design frequency bands and support sufficient current, we built a high-efficiency full bridge rectifier to rectify the high-frequency signal into DC signal. Additionally, to support device mobility or charging in different areas, high power transfer efficiency requires real-time device location to adjust the charger's mode and meta-surface configuration. Prior work have shown that localization can be done by tuning meta-surface units without extra hardware. However, current methods rely on controlling all units at once, which causes significant delays. In this work, we propose a fast method that only needs to manipulate a single unit, significantly reducing the control complexity. We first determine the projection coordinate of receiver coil on meta-surface. We then activate each meta-surface unit sequentially and detect peak power transfer efficiency. When the receiver coil is projected onto a certain working unit on the meta-surface or is closest to that unit, the power transfer efficiency is at its strongest, regardless of the orientation or distance of the receiver coil relative to that working unit. Once the projected coordinate of the receiver coil is known, we can use the pre-calibrated relationship between capacitance and angle to calculate the deflection angle between transmitter coil and the receiver coil. Given the deflection angle between TX and RX coil, we can further estimate how far the receiver is away from the transmitter based on the angle distance PT diagram. Finally, we built a prototype system of charge M, incorporating the coils, meta-surface, source circuit, and load circuit. Finally, we tested with smartphones. We first measured how long it took to fully charge a smartphone with different distances and compare charge M with both commercial wireless chargers and the other advanced prototypes. We use 20 watts of transmit power for our standard. The results show that Charge M outperforms both commercial systems and the state-of-the-art prototypes. Its charging distance is up to 2 meters. Next, We test the system under different deflection angles between the TX and RX coil. ChargeM is able to deliver the most consistent power to the RX in all orientations, even though the RX coil is orthogonal to the TX coil, thanks to its beam focusing ability, which is similar to the behavior of two other advanced prototypes. In the meantime, we conduct experiments with multiple smartphones in different areas and distributions. The smartphones used in this experiment include different models. The results demonstrate that ChargeM can simultaneously charge multiple phones regardless of their model or whether the users are in the near field or far field. The maximum charging devices is up to 5. Finally, to validate the accuracy of the proposed localization method, we conduct experiments by varying the number of receiver devices and assess the impact of different distance between them. The results show that ChargeM achieves acceptable localization accuracy with up to 5 devices. Additionally, we find that a spacing of 20 centimeters between receivers yield the optimal performance. To conclude, ChargeM enables distance-adaptive wireless charging by switching between near and far-field modes. It achieves charging distance of up to 2 meters with a low transmit power of 20 watts. It supports multi-device charging and it's robust to the device's orientation. Thank you.